Hello. In this video, I'm going to be solving the following initial value problem using the Laplace transform. And the initial value problem of interest is this one right here, where A and B are just constants. We don't know what they are. Okay. Some of my students might wonder whether this problem is from our notes, which are the Yuri level notes on DiffyQs, but this one is not. This is a problem of my own making. And so don't worry if you can't find this in the notes. It's not in the notes, but it will be here in this YouTube video. Okay, so we want to solve this IVP using the Laplace transform. But in order to be able to use the Laplace transform, we need to know how the derivative of a function affects its Laplace transform. Because the basic idea here for solving this, and I'll write this in blue, actually. The basic idea for solving this equation will be to apply the Laplace transform to both sides. And, well, what does this look like? Well, it's going to be L of x double prime plus x equals L of e to the t. And so then, just by using linearity, we're going to compute the Laplace transform of x double prime plus the Laplace transform of x. And, well, from an earlier table that we saw in our previous video from this week, we know that the Laplace transform, I'll write this in purple, of e to the negative at equals 1 over s plus a. And so the Laplace transform of e to the t is going to be 1 over s minus 1 in this case. And okay, so the idea is we're going to let x of s be the Laplace transform of our function s, of the function we're trying to solve for. So we get L of x double prime plus x of s equals 1 over s minus 1. And our goal is going to be to solve for x of s. But we can't do that yet because we don't know what L of x double prime is. And so let me write this down. Because once we solve for x of s, we'll be able to take the inverse Laplace transform and find the solution to our original ODE. To find the solution x of t. But first, we need to determine what is the Laplace transform of x double prime. And for this, we're going to use a general property about Laplace transforms of derivatives. So key property, if f of t, or rather if the Laplace transform of f of t equals f of s, then the Laplace transform of the derivative of f of t is going to be exactly f of s minus f, little f in this case. That's very important. It's not capital F. Here we're doing little f. And we're plugging in 0. Now this assumes that our function little f is defined at least on an interval containing 0. So that's what we're assuming here. And, well, why is this useful? Well, because now we can, once we know what the Laplace transform does to the first derivative, we can work out what it does to the second derivative. So notice it follows that the Laplace transform of f double prime of t is going to be, well, now using this formula, so, okay, it might be clearer if I write it this way. This is going to be f prime of t prime. So using this formula here, what we see is that the Laplace transform of the second derivative of t is going to be s times the Laplace transform. And I'm going to write this in blue too. So this is the Laplace transform of f of t. So we're just applying this formula here for the Laplace transform of the derivative. But instead, our little f is actually f prime. And so therefore, our capital F is going to be the Laplace transform of little f prime. So this will be Laplace transform f prime of t minus, and oh, actually, maybe that's not the best way to explain it. Because now now we would have to calculate f prime of 0. Oh no, actually that's fine. Sorry, what am I saying? So ignore what I just said. There's no issue here. So again, we have this formula, but now we know what the Laplace transform of f prime of t is because we found it right here using this previous formula. So we could just plug in this into here to get f of s minus f of 0. And then we're going to get minus f prime of 0, which simplifies to be s squared f of s minus little f of 0, minus f prime of 0. And in general, if you want to work out the Laplace transform of higher order derivatives, you would just use this rule recursively, plugging in your higher derivative on the left side, and then the Laplace transform of the lower derivative for capital F of s here. Okay. Why is this useful to us? Well, for us, with this calculation we just did, we get that the Laplace transform of x double prime is going to be s squared capital X of s minus s times little x at 0 minus x prime at 0. And so, but because we know what these values are, again, we were given that x at 0 should be a, x prime at 0 should be b. This is going to be s squared capital X at s minus as minus b. So from star, so I'm going to denote this equation by star right here. So from star, we get that s squared x at s minus s, or as, minus b, plus x at s is 1 over s minus 1. And so moving on to the next page, so let me just copy what we had. We had this. We had s squared x at s minus s, or as, minus b, plus x at s equals 1 over s minus 1. We can then proceed to solve for this function right here. So collecting like terms, we get x squared plus 1, capital X at s. And then if we add both of these terms to the right side, we're going to get as plus b plus 1 over s minus 1. And so, because this left side is never 0, at least when s is real, we can divide by s squared plus 1, and we get the Laplace transform. It's going to be as plus b all over s squared plus 1 plus 1 over s squared plus 1 times s minus 1. Very nice. Okay, so this gives us the Laplace transform of our function. But now we need to find our original solution, x at t. So now we take or we want to take. And you know what, actually, I'll write this a bit later. So the goal is going to be to apply the inverse Laplace transform to the right side. But to do this, we should get it in a way where we recognize where we break it up into pieces, and each of these pieces are such that we know its inverse Laplace transform. Now for this, we need to do partial fraction decomposition here, and just sparing the details. So, okay, breaking up this fraction, I get a times s over s squared plus 1 plus b times 1 over s squared plus 1. And then if you do partial fraction decomposition on this term right here, you're going to get plus 1/2 times 1 over s minus 1 minus 1/2 times s plus 1 over s squared plus 1. Okay. And now we just need to split up this right side. So this will be as over s squared plus 1 plus b times 1 over s squared plus 1 plus 1/2 times 1 over s minus 1. And then we have minus 1/2 times s over s squared plus 1 minus 1/2 times 1 over s squared plus 1. Okay. Now, some of you might see why I'm doing this. So some of you with some inverse Laplace transforms under your belts might recognize what these expressions are, but we'll get to that in a bit. So, okay, continuing on to combine like terms, I'm going to collect these terms together. So this is going to be a minus 1/2 s over s squared plus 1. And then I'm going to have plus b minus 1/2 times s over s squared plus 1, and then plus 1/2 times 1 over s minus 1. Great. So once again, we have the Laplace transform, but we want our original function x at t. So now we take inverse Laplace transforms to get x at little t. So x at t is going to be the inverse Laplace transform of capital X at s. And by linearity, this is a minus 1/2 times the inverse Laplace transform of s over s squared plus 1 plus b minus 1/2 times, and let me move all of this over, times inverse Laplace of 1 over s squared. Oh, this is supposed to be a 1. Oops. Plus 1, and then plus 1/2 inverse Laplace of 1 over s minus 1. And all that remains is to figure out what these inverse Laplace transforms are. But as a reminder to everyone, in general, the inverse Laplace transform of s over s squared plus a squared equals cosine of at. The inverse Laplace transform of a over s squared plus a squared equals sine of at. And finally, we have the inverse Laplace transform of 1 over s plus a, and this is e to the negative at. And let me just go to my table, make sure I have this right. Yeah, I do. And so applying these formulas, well, we can go over here and we get a minus 1/2 times, okay, so here my a is 1 for this formula here, so I'm going to just get cosine of t. And similarly, a is 1 for this formula here, so I'm going to get sine of t plus b minus 1/2 times the sine of t, and then plus 1/2. And here I'm doing the inverse Laplace, and let me clean it up just to make it a bit nicer. The inverse Laplace of 1 over s minus 1. And just looking at this formula here, we're going to get e to the t, so this will be 1/2 e to the t. And thus, this is the exact solution to my original IVP right here. Notice how easy this was to solve compared to the usual thing where we would have to do undetermined coefficients, and then we would have to solve for the constants individually using like linear, by solving the resulting linear system. We were able to sidestep all that using the Laplace transform to immediately get the solution here. Pretty neat. All right, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.